Hello everybody, today we're going to do experiment about the shell and tube heat exchangers. Also we can see here we have spirit heat exchangers and concentric heat exchangers. But this day we're going to focus about the shell and tube heat exchangers. Now, so come with the unit for the safety part. So this, as I speak before, this one thing is for the storage of the hot water, and you have to be much careful about it. As I introduced before, the water is the most important things here, and now we have two tanks. The first tank is the heat exchangers, and another tank is for the cold water. And as I mentioned before, this tank is about the cold water, and also one more thing, you have to be careful of it, or is the flow of the water, and you have to control it.
So now in my part, I'm going to introduce which valves are open and which valves are closed. And in counter current shell. Okay, when it comes on counter current shell, the cold water enters the shell, which is this one, at room temperature, and the hot water enters in opposite direction. So to think that situation, we need to close the valves 15 and 18, which are already closed, and also we need to open valve 16 and 15. So we need to open those valves. After that, we will switch on the pump 1 and pump 2. Then we will take the readings of the flow rates. So after that, we will do the co-current shell. Okay, for co-current, we need to close two valves, which is valve 16 and valve 17. So we need to close it now. And also we need to open valve 15 and valve 18, so which was open in counter current shell. So now that is the situation that we need.
Now to take the readings of the temperatures, first we have to set the flow rates of the hot part and the cold part. So we have here in the hot part and the cold part of the flow rates. So first time we have to fix this one, the 10 lpm. Then we have to fix it the cold water to 1 time to 2, 1 time to 4, 1 time to 6. So when we fix it to, we have to take the readings. So first we have to make sure that this temperature controller is 50 Celsius. Then we can take the readings of T1 when it's stable. The temperature, the flow rate is stable. So we can take temperature 1, 2, 3, 4. And again, we will do another set of the same co-counter current. So now we change the flow rate. Now we will change the hot part to 2, 4, 6 until 10, but we will fix it the cold part in 10 lbm. So again, we will do the same thing. We just make sure that temperature controller is 50 Celsius. Then we'll take when it's steady state, we take the temperature TT1, TT2, TT3, TT4. That's all.
Okay, hello everyone. So right now we're in the calculations part. So in this calculations, we have the table, and the table we recorded the values, which are these, the T1, T2, T3, T4, and so on. So from these values, we use these values to do our calculations. So this calculation is not did by us, it's did by Jasmine's group, and we're gonna give them a tribute with them. So over here we have the mass flow rate. So mass flow rate is given in liter per minute. So liter per minute, we have to change it to kilogram per second. So we converted it through this method, and therefore we got the 0.167 kilogram per second and 0.033 kilograms per second. So that is the flow rate converted to kilogram per second for that equation. So right now we're gonna move on to the Q hot and Q cold. So in order to get our Q loss, we have to find the Q hot and Q cold. Okay, so from this equation we have Q hot and Q cold. So Q hot and Q cold is needed to calculate our Q loss, which is Q hot minus Q cold. So from this we use the formula Q equals to MC delta T to find our value, which is 1.05 kilowatts. So after that we found Q hot, and we use the same thing for Q cold. For Q cold we did the same calculations, and we got 0.46 kilowatts, where we substitute inside this equation Q loss equals to Q hot minus Q cold. Therefore, we got 0.59 kilowatts. So that is done. We're going to find the percentage of error for Q. So percentage of error for Q is Q hot minus Q cold over Q hot times 100%. So we did the calculations and we have a percentage of error of 56.19%, which is but anyways, we're gonna move on to the Q average. So the Q average is we just needed this to make sure that our values our reading is not far off from the original one. So we have 0.76 kilowatts. Alright, so next, so continuing, the delta T1 and Lm, which is delta T1 minus delta T2 over ln delta T1 over delta T2. So that is the equation, and we just sub in the values of delta T1, which is delta T1 minus T4, so you get 20.6 degrees Celsius, and we sub in, same goes for delta T2, which is 15.8 degrees Celsius. So yeah, therefore we have the delta ln m, which is 18.09 degrees Celsius. That is done for the delta T. Before we continue on to find our U, we have to find our average surface area. So the average surface area, the equation for it is the outer surface area plus the inner surface area over 2. So before that, we have to find the inner surface area and the outer surface area. So the outer surface area, we have delta T equals to pi dl, and then we have we substitute all the equations, and we got the value, which is 0.015 meters squared. And then same goes for the inner surface area. We use the same formula, and we got 0.012 meters squared. And then from that, we just substitute the outer surface area value and the inner surface area value into this equation, and we have the average area, which is 0.0135 meters squared. And from that, we are able to find our U. So the U, which is Q average over A average times delta T ln m. We just substitute all the values that we use here into this equation, and we have our final value, which is 0.11 kilowatts over meter squared degrees Celsius. So that is all for our calculations part. We're gonna move on to.
Now at the end, it is the end of our experiment, and in conclusion, I'm going to explain two equations. And now let's move to explain. The first equation is Q equal to U and the area times the delta T. The second one will be U Q divided by A and delta T. Let's start with the first one. In the first one, we can see that as long as Q is connected proportionally to U, so if U will increase, once U will increase, means the Q will increase. But in the second one, we can see that U and delta T is inversely proportional. So once delta T increase, the U will decrease. And from our calculated data, we can see that it is fluctuating in increasing and decreasing between U and Q. And finally, U will follow the highest rate. For example, if the U here increased more, if the Q is increased, the U will be increasing. If the delta T was more, has more value, the U will get less value. And that's all of our